This video is going to be a quick recap of the key things about inverse trig functions that you learned in Calc 1 that we're going to need to use in Calc 2. So first, let's just think about a basic trig function. Let's look at tangent. Okay, so if we were going to find the inverse function for tangent, if you recall, in order to find the inverse of a function, graphically what we're going to do is reflect it over the line y equals x, because we're going to exchange the x's and the y's. But when we do that, we want to end up with something that's still a function. So we first have to restrict our domain to places where this tangent function is going to pass the horizontal line test. So notice, it's not passing the horizontal line test here because it's crossing my graph 3 times. So instead, we're just going to restrict my domain. And the default that we use for tangent is just going to be between negative pi over 2 and pi over 2. And so you can see if we just restrict tangent to be between there, then when we reflect it over the line y equals x to find the inverse tangent, we're going to have something that is actually a function. And this graph of this inverse tangent is one that will come up throughout Calc 2, so it's really good to have this picture in your head. And you can see that this is going to be bounded by, the biggest that it'll ever be, is going to be pi over 2. And again, the smallest, and it never actually reaches pi over 2. So its upper bound is pi over 2. That's going to be a horizontal asymptote. And then its lower bound is negative pi over 2. That's also a horizontal asymptote. Okay, so that means that anytime we see the notation y is equal to arctan of x. And just to note, the equivalent notation is we can also write this as inverse tangent. So it looks like tan to the negative 1. It's not that I'm writing 1 over tangent of x. This is literally just notation that means the same thing as above. It means I'm taking the inverse. And again, when you read this, instead of saying y is equal to arctan of x, I want you to say, well, what tangent of what angle is going to give me x? Because that is exactly what this inverse tangent function means. Okay, and we do the same thing for all the other trig functions, but there's really only one other one that is going to come up a ton in Calc 2. So let's do that other one. That one's going to be arcsine. Okay, so let's do the same thing for sine. So let's think of our graph of sine. But then notice again, we're going to have to restrict our domain to where it will pass the horizontal line test. So our convention, the default that we do, is going to be to restrict it between negative pi over 2 and pi over 2. Here and here. Okay, and by restricting the domain of sine of x to be there, so that's sine of x, then when we flip this over the line y equals x, that means that our range of arcsine is what's going to be between negative pi over 2 and pi over 2. And that's, you can see that right here, that's going to be pi over 2 and that's negative pi over 2. And so again, when you read this notation, you're thinking of sine of what angle gives me x. Now we're going to practice using reference triangles to simplify this expression, and this is going to show up actually when we're taking derivatives, which we're going to do next, and it's also going to be showing up when we're learning a new integration technique in a couple lessons called trig substitution. So the first idea here is let's just let theta be inverse tangent of x. So that means that tangent of theta is x. And let's think carefully about what theta can be. As we recall from our graph of the inverse tangent function, theta is going to be restricted to between negative pi over 2 and pi over 2. So now we're going to draw a reference triangle, and the default reference triangle that we usually draw is assuming that theta is between 0 and pi over 2. So we'll consider that case first, and then we'll come back to the case where theta is between negative pi over 2 and 0. So if we draw the reference triangle here, here's theta. Since tangent is x, we can really think of this as being like x over 1. And if you recall, tangent is opposite over adjacent when we're thinking of the definition of trig using the unit circle. And so that means I'm going to have opposite is x, adjacent is 1, which then gives me my hypotenuse is square root of x squared plus 1 from the Pythagorean theorem. And that means I can now find secant of this angle. So that tells me secant of this angle is 1 over cosine. So instead of adjacent over hypotenuse, it's going to be hypotenuse over adjacent. Okay, now just check. This is the time where we want to check the signs that we get of our answer here. So the way I've written this, my answer here is always going to be positive because I have a square root over 1. And so I just need to check, is secant always going to be positive for these values of theta? And if you remember, cosine between negative pi over 2 and pi over 2 is always positive. So secant will always be positive. So I know that I have the correct sign here, the correct SIGN here. I know that it's always positive. And that means, in this case, I'm going to square it, so it doesn't really make that big of a difference. But in the next problem we're about to do, we have to be careful about what happens for different values of theta. Okay, so at the end, I get that secant squared is this, and then remember we let theta be inverse tangent. So that's the same as writing it just like this. Okay, so now you're going to try the next two. Okay, so now go ahead and put this on pause, and you try both of these using reference triangles. Okay, so for the first one, let's let theta be my inverse sine, and that means that I have this for theta between negative pi over 2 and pi over 2. So that means my reference triangle, sine is opposite over hypotenuse, and so that means this side has to be the square root of 1 minus x squared. And now that means, according to this, I can take the cosine of this angle, and I'm going to get square root of 1 minus x squared over 1. And now again, let's do a check to make sure I have the correct sign, S-I-G-N, not sign, S-I-N. And notice the way I've written this will always be positive. And then we just go and check. Is cosine of theta always going to be positive for these values of theta? The answer is yes. So we know we're done. That means that cosine of my inverse sine of x will be the square root of 1 minus x squared. Okay, and lastly we have this one, so let's let this be theta. Okay, and then we'll draw a reference triangle. And again, because we're interested in cosine of theta, on this interval, we know this should always be positive. And so we're just going to take that into account. First, let's just think of theta as being between 0 and pi over 2. So then this reference triangle, opposite over hypotenuse, or no, opposite over adjacent, here, opposite over adjacent, is going to give me square root of 1 plus x squared for my hypotenuse, which means that cosine is going to be adjacent over hypotenuse. Okay, so this will work out fine if my theta is between 0 and pi over 2, because we know in that case that tangent of theta would be positive, so that means x is going to have to be some positive value, and this whole thing will be positive. If theta is between negative pi over 2 and 0, then my tangent is going to be negative, which means x will be negative. But we know that cosine always has to be positive on that interval, so in order to account for that, I need an absolute value here. And then I'll make sure I always have the correct sign, regardless of what my angle is between negative pi over 2 and pi over 2. Okay, so this is actually going to make finding these derivatives really quick. The trick here, again, is to rewrite this in terms of tangent of what angle is going to give me x, and then we can use implicit differentiation. So take the derivative of both sides with respect to x. So I'll have the derivative of tangent secant squared, and then from the chain rule I have times dy dx. And then this derivative of the right-hand side with respect to x is just 1. And then we're going to solve for dy dx. And this gives me 1 over secant squared y. But this should be looking familiar because this is 1 over secant squared of inverse tangent of x. But we did this. This was part A of the previous example, and we got, using the reference triangle, that this is just x squared plus 1. So this whole thing is going to be 1 over x squared plus 1. Okay, so your turn. Put this on pause, and you find what the derivative of arc sine is. Okay, same idea. So we're going to say that sine of y is x, and then we're going to take the derivative of both sides with respect to x using implicit differentiation, and that's going to give us that dy dx is 1 over cosine y, but that's exactly what we just found in the previous example, part B, because this is the same as cosine of inverse sine or arc sine of x, and we found that that denominator is just going to be the square root of 1 minus x squared. And so that is the derivative. So that's a quick summary of some of the things you need to know about inverse trig functions.